Welcome back. Let's practice using the chain rule for multivariable functions. All right, so here's our first example. We want to find dw dt, or the derivative of w with respect to t, using the chain rule. And we are given w is equal to x² minus y², where x is equal to 2t and y is equal to 3t. Okay, so if we want to find the derivative of w with respect to t, we do want to make use of the chain rule, as the problem tells us. But the formula for the chain rule of multivariable functions looks different depending on the variables that you are working with. Because for what we've been given here, there are three different types of variables. W is the dependent variable. It is what is used for the main function here that is also a multivariable function. But that dependent variable w is defined in terms of two other variables, x and y, which we would classify as intermediate variables, because each of those variables are defined in terms of another variable, which would be the independent variable. All right, it's the variable we want to find the derivative of w with respect to. Those intermediate variables, x and y, act as bridges or pathways from the dependent variable to the independent variable. All right, so we have two intermediate variables, but just one independent variable. And so our formula for the chain rule will look different here than it would if we had more than two intermediate variables or more than just one independent variable. Okay, so to help us build the formula for the chain rule that we will use in this example, I recommend that you draw a derivative tree. And to do that, you want to start by writing down the dependent variable, which in this case is w, and then identify the different intermediate variables. In this case, they are x and y. So from w, you can branch out to the intermediate variable of x, represented by this equation, and the other intermediate variable y, represented by this equation. All right, and then both of those intermediate variables are defined in terms of one independent variable. So x is defined in terms of t, and y is defined in terms of t. And so from this diagram, or this tree, we can put together the formula for dw dt. And so here's what that will look like. dw dt will be equal to the sum of two terms that we will get from this tree. We'll get one term for each of these different paths that we can take. So starting at w, we have a choice of either going to x or to y, meaning that we can take a partial derivative of w with either respect to x or y. So let's start by taking a partial with respect to x. And so we have the partial of w with respect to x, and then that will be multiplied by the derivative of x with respect to t, right? We go from w to x, that is a partial derivative, and then we take the derivative of x with respect to t. That is just a regular derivative, not a partial derivative, because x is only defined in terms of t. We have no choices here. We can only take one type of derivative of x. Okay, so we'll multiply this partial derivative by dx dt, and then we will add that to the other term that we get by taking the other path. Because while we can take a partial of w with respect to x, we can also take a partial of w with respect to y. That is the other choice that we have here. So we'll have a partial of w with respect to y, and then that will be multiplied by the derivative of y with respect to t. Again, that is our only option because y is only defined in terms of one variable. So we will be taking a derivative of y with respect to t. All right, so we will have dy dt. And that is the formula for the chain rule that we will use to find dw dt in this example. And this is probably also the most common form of the chain rule that you will use, but it can look different if you do have more than two intermediate variables or one independent variable. All right, but now that we have the formula set up, let's find dw dt. We need to find all these different derivatives and then perform these calculations. So let's do that here, starting with the partial derivative of w with respect to x. So looking at what w is equal to here, if we're taking a partial with respect to x, we're treating y as a constant. So this negative y squared would just be a constant whose derivative is 0. So just take the derivative of x squared and you'll get 2x. And then you want to multiply that by the derivative of x with respect to t. And so looking at x here, we have 2t. The derivative of 2t with respect to t would just be 2. The coefficient of t to the first power. So we're multiplying 2x by 2, and then we will add that to the partial derivative of w with respect to y. So going back to the equation for w here, we're now taking a partial with respect to y, so treat x as a constant. So this x squared term would be a constant whose derivative is 0. But then the derivative with respect to y of negative y squared would be negative 2y, and that will be multiplied by dy dt, or the derivative of y with respect to t. And so with respect to t, the derivative of 3t is 3, the coefficient of that t to the first power. So we'll multiply by 3, and now we have found all of those derivatives. Now we just need to simplify, and we will have dw dt. And 2 times 2 is 4, so we get 4x, and then negative 2 times 3 is negative 6, so we get minus 6y. And that right there would be an acceptable answer for dw dt. That would be the derivative of w with respect to t. It doesn't really look correct at first because it's in terms of x and y, but remember that both x and y are expressions of t. Okay, so while this is an okay answer, if the expressions are simple enough, I do recommend that you try to get this answer entirely in terms of t by substituting in what x and y are equal to in terms of t. All right, so in this case, we would have 4 multiplied by x, which is 2t, so 4 times 2t minus 6 times y, where y is 3t. So we have 6 times 3t. And so simplifying, 4 times 2 is 8, and 6 times 3 is 18. So this is equal to 8t minus 18t, and 8t minus 18t is negative 10t, so this is equal to negative 10t. And that right there is the derivative of w with respect to t, or dw dt. Okay, let's take a look at another example. For our next example, we want to find dw dt using the chain rule and evaluate at t equals pi. And we are given w is equal to x times e to the power of y, where x is equal to sine t and y is equal to pi minus t. Okay, so there's 2 parts to this example. We want to find the derivative of w with respect to t again, just like we did in the previous example. But then once we have that, we also want to evaluate it at this specific value of t equals pi. So we'll do that then, but let's focus on the derivative to start. And looking at the equations that we've been given here, we still have one dependent variable. You always will. That will not change. W is our dependent variable, and it is defined in terms of 2 intermediate variables, x and y. And then both of those intermediate variables are defined in terms of 1 independent variable, t. So our derivative tree here will look just like it did in the previous example. We still have w, which you could take a partial derivative of with respect to either x or y, the 2 intermediate variables, which are then defined in terms of 1 independent variable, t. So both x and y you could only take a derivative of with respect to t. So those would be regular derivatives, not partial derivatives. Okay, so to find dw dt, we will set up the same chain rule formula. We'll start by taking a partial of w with respect to x and multiplying that by the derivative of x with respect to t. So we have the partial of w with respect to x multiplied by dx dt, and then we will add that to the partial derivative of w with respect to y, and then multiply that by the derivative of y with respect to t. All right, so we have the partial of w with respect to y multiplied by the derivative of y with respect to t. Okay, so let's set this up. Let's find all of these derivatives to find dw dt. Starting with the partial of w with respect to x, looking at w here, we have x to the first power times e to the power of y. With respect to x, e to the power of y would just be a constant. So the derivative of x to the first power would just be equal to its coefficient, or the constant multiplied by it. So for the partial of w with respect to x, we do just get e to the power of y, and then that will be multiplied by the derivative of x with respect to t. So looking at x here, the derivative of sine t with respect to t would be cosine t. So we are multiplying by cosine t. And then we will add that to the partial derivative of w with respect to y. And so looking at w here, x would now be the constant, and e to the power of y is what we would want to take the derivative of. And the derivative of e to the power of y is just itself, so nothing changes here. You keep that same coefficient and just rewrite the exponential function. So we have x times e to the power of y, and then that would be multiplied by the derivative of y with respect to t. So looking at y here, pi, that's just a constant value, so its derivative is 0, and then the derivative of negative t is negative 1. So we're multiplying by negative 1. Okay, and then simplifying, we get e to the power of y times cosine t minus x times e to the power of y. Now, this would be the derivative dw dt, but if you wanted to, you could get it entirely in terms of t by replacing y and x with what they're equal to in terms of t. And so I'm going to do that here, but an alternative approach that you could take is to just leave this answer like this, and then when you go to evaluate the derivative at this value of t, just remember that y and x are in terms of t, so you could plug this value of t into each of those expressions, and then whatever they're equal to, you could put right into your evaluation. I'm not going to do that here. Instead, I'm going to rewrite this derivative in terms of t, and then plug in pi for t. Okay, so remember, y is equal to pi minus t, and x is sine t. So we get e to the power of pi minus t times cosine t minus sine t times e to the power of pi minus t. All right, and so that is dw dt, but then let's evaluate it at pi. So we'll have dw dt evaluated at t equals pi will be equal to e to the power of pi minus pi times cosine of pi minus sine of pi times e to the power of pi minus pi. Now pi minus pi is 0, and e to the power of 0 is 1. So this will simplify to 1 times cosine of pi, which is a negative 1, minus sine of pi, which is 0, times 1, which is just 0. So you're subtracting 0, and so really you just have 1 times negative 1, which gives you negative 1. That is the evaluation of dw dt at t equals pi. Okay, and again, if you left your answer in this form and you didn't write it entirely in terms of t, you could have plugged pi in for t in these expressions for x and y, and x would have been equal to 0, and y would have been equal to 0. So you could have plugged 0 in for x and y right into this expression to evaluate dw dt at t equals pi. That's the other option, but I decided to express dw dt entirely in terms of t and then plug in. But again, assuming that the problem doesn't explicitly tell you to get it in terms of t, the way that you go about this is up to you. Next up, we want to find dw dt using the chain rule, and we are given w is equal to x to the power 4 times y plus 2x squared times y cubed, where x equals 5 plus t squared and y equals 7t cubed. Okay, so once again, the first thing you want to do here is determine what your chain rule formula will look like for your given function. And in this case, we have one dependent variable w that is defined in terms of two intermediate variables, x and y, which are then defined in terms of one independent variable of t. So once again, we're going to be using the same formula that we used in the previous two examples. Our derivative tree looks exactly the same. We'll start with the dependent variable of w, which you could then take a partial derivative of with either respect to x or y, the two intermediate variables, and both x and y are defined in terms of one independent variable of t. Okay, so the derivative of w with respect to t, or dw dt, will be equal to the partial derivative of w with respect to x, that's this derivative here, and then we will take a derivative of x with respect to t. Specifically, we will multiply by that derivative dx dt. Then we will add the other path from the tree, where we take a partial derivative of w with respect to y and multiply that by the derivative of y with respect to t. So we have the partial of w with respect to y multiplied by the derivative of y with respect to t. Okay, so now that we have the formula, let's find dw dt, starting with the partial of w with respect to x. And so looking at w here, there are two terms to take into account. And remember that we are treating y as a constant. And so for the first term here, this y would be a constant. So just take the derivative of x to the power of 4 and leave y alone. So using the power rule, we get 4x to the power of 3 times y. All right, and so that was the first term. But then for the second term, y cubed would just be a constant. So keep that the same and just take the derivative of 2x squared. Using the power rule, you will get 4x to the first power multiplied by y cubed. Okay, so that's the partial with respect to x. and that will be multiplied by the derivative of x with respect to t. And so looking at x here, 5 is a constant, so its derivative is 0, and then the derivative of t squared with respect to t is 2t. So we will multiply by 2t, all right? And then we will add that to this term. So starting with the partial of w with respect to y, let's look at w here. X to the power 4 would just be a constant, or the coefficient of y to the first power, so its derivative would just be x to the power 4. And so we'll have x to the power 4, but then don't forget about this term. 2x squared would just be a constant. It's the coefficient of y cubed. So using the power rule for derivatives on y cubed, you'd multiply that 3 down. 3 times 2 is 6. Subtract 1 from that exponent, and you'll have plus 6x squared times y squared. And so that's the partial of w with respect to y. And then finally, you want to multiply that by the derivative of y with respect to t. And y is equal to 7t cubed. So just use the power rule for derivatives here. Multiply that 3 down, subtract 1 from the exponent, and you get 21t squared. Okay, and so now let's simplify our answer here, starting by distributing 2t through this quantity. So multiply it by both of those terms. This would be equal to 8 times x cubed times y times t plus 8 times x times y cubed times t. And then that would be added to 21t squared distributed through this quantity. So multiply it by both of those terms. And you'll get 21 x to the power 4 times t squared plus 6 times 21 is 126. So we have 126x squared, y squared, t squared. And that right there is our final answer. This is dw dt, the derivative of w with respect to t, and I'm going to leave it in this form this time around. Technically, you could go further and get it entirely in terms of t by replacing all of these x's and y's with what they are equal to from these two equations, but as you can probably tell, that will get very messy very quickly. And so I'm not going to do that here. There's no reason to do it unless it's very easy to simplify like it was in the previous two examples, but in this case, that is not going to be worth our time. So it's fine to leave the derivative in this state unless you were told to get it entirely in terms of t. Otherwise, this is fine and would be our final answer. Okay, so if you want to have some fun, feel free to go ahead and plug these different expressions in for x and y in this expression and simplify. But with that, that is it for this example. Let's take a look at another one. Next up, we want to find dw dt, or the derivative of w with respect to t, using the chain rule, and we are given w is equal to z times sine of x plus y, where x is equal to t squared, y is equal to t minus 1, and z is equal to t cubed. Okay, so this example is a little bit different than the examples we've looked at so far. Notice that w this time around is defined in terms of 3 variables. We have x, y, and z. So now there are 3 intermediate variables that are all defined in terms of one independent variable t. Okay, so the derivative tree that's going to help us set up our chain rule formula will look a little bit different this time. We still have the same dependent variable of w, but we can take a partial derivative of w with respect to each of those intermediate variables, right? We have x, y, and z. You can take a partial of w with respect to each of them, but then each of those intermediate variables are defined in terms of just one independent variable of t. So for each of them, you can only take a regular derivative with respect to t. Okay, so here's what the chain rule formula will look like this time around. We're still taking a derivative of w with respect to t, and it will be equal to the sum of 3 different terms, one for each of the 3 different paths that we can take from w in this tree. We have a choice of moving to x, y, or z, so all 3 of these derivatives will be partial derivatives. We can take a partial of w with respect to x, y, or z. Starting with x, we have the partial of w with respect to x, and that will be multiplied by the derivative of x with respect to t. So we have dx dt, and then we'll add that to the term for the second path. We'll take a partial of w with respect to y and multiply that by the derivative of y with respect to t. So we get the partial of w with respect to y times the derivative of y with respect to t. And now we're not done yet, because unlike in our previous examples, there is another intermediate variable. We want to add another term But for the third path of this tree, where we take a partial of w with respect to z, and then take a derivative of z with respect to t. So we get a partial of w with respect to z times the derivative of z with respect to t. Okay, and so that is how we will find dw dt for this function. And so let's start working on it. Let's begin by finding the partial derivative of w with respect to x. So looking at w here, x is inside the sine function, so we will have to make use of the chain rule from calculus 1, which technically it's the same chain rule, but in a situation where there's only one intermediate variable. But anyway, we have to take the derivative of the outside function, keeping the same inside function, and then multiplying by the derivative of the inside function. And we're still going to keep that z out front because we would just be treating it as a constant since we're taking a partial with respect to x. So we have z times cosine of x plus y, right? The derivative of sine is cosine. So you have cosine of that inside function, and then you would want to multiply by the derivative of the inside function, but in this case, it would just be 1, right? The derivative of x is 1, and then we're treating y as a constant. Its derivative would be 0. So the derivative of the inside function is 1. So we're multiplying by 1, which doesn't change anything. So I'm just going to leave the partial derivative like this. But then that would be multiplied by the derivative of x with respect to t, and x is equal to t squared, so the derivative of that with respect to t would be 2t, so we're multiplying by 2t, and then that would be added to the partial derivative of w with respect to y, which will be very similar to the partial derivative of w with respect to x. In fact, it's exactly the same. Since y is inside the sine function, we do need to use that calc 1 chain rule, so keep that coefficient out front, and you'll have z times the derivative of sine, which is cosine, keeping the same inside function of x plus y, and then the derivative of the inside function is still 1. The derivative of x with respect to y is 0 because we're treating x as a constant, and then the derivative of y is 1. So you're still multiplying by 1, nothing changes there, but then you do want to multiply by the derivative of y with respect to t, which in this case y is equal to t minus 1, and the derivative of t with respect to t is 1, and the derivative of negative 1 is 0 because it's a constant. Okay, so we're still multiplying by 1. I will write that down here just so that you can see what dy dt is equal to. But then we have one more term to take care of. We need to add the partial derivative of w with respect to z. So looking at w, this partial derivative will be different than when we took a partial with respect to x or y because z is not inside the sine function. So sine of x plus y with respect to z is a constant. And so just take the derivative of z to the first power, that would be equal to its coefficient, or the constant being multiplied by it, which in this case is sine of x plus y. So we get sine of x plus y, and then that will be multiplied by the derivative of z with respect to t. And if you look at z here, z is equal to t cubed, so taking the derivative of that using the power rule, we get 3t squared. Okay, and so then all there's left to do is simplify. And there's really not much simplifying to do, just maybe some reordering of multiplication of different parts. So for the first term, we'll have 2z times t times cosine of x plus y, and then we have plus z times cosine of x plus y, and then plus 3t squared times sine of x plus y. And that would be my final answer for dw dt. Once again, if you wanted to get it entirely in terms of t, you could do that. You could replace all of the z's, x's, and y's that you see in this expression with what they are equal to from these equations, but I'm not going to bother to do that here, as it would make things more complicated, although it's not as bad here as it would have been in the previous example. So if you want to try to get everything in terms of t, feel free to do that, but it's ultimately not necessary, so I will leave my final answer like this. Okay, let's move on to the next example. Hey, real quick, before we take a look at the next example, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. For this example, we want to find the partial derivative of w with respect to s and the partial derivative of w with respect to t using the chain rule. And we are given w is equal to x²+y²+z², where x is equal to t times sine s, y is equal to t times cosine s, and z is equal to st². Alright, so right away from the directions themselves, you can tell that this problem is a little bit different than what we've done so far. The giveaway is that we want to find two partial derivatives for w rather than a single derivative. And the reason that makes sense here is because, well, w is in terms of three intermediate variables, that's nothing new, but the intermediate variables themselves are defined in terms of two variables now. There are two independent variables of s and t. And so because there are two independent variables, we can't just find one singular regular derivative for w, we can only find partial derivatives. We can find a partial derivative with respect to each of the independent variables s and t. Alright, and that will be made clear when we draw out our derivative tree. So let's do that here. We still have a single dependent variable of w. That will always be the case, but then we have three intermediate variables to take into account. We have x, y, and z. So from w, we can take a partial with respect to x, with respect to y, or with respect to z. And then for each of those intermediate variables, there are two independent variables of s and t. So from x, you could take a partial with respect to s, or take a partial with respect to t. And you could do the same thing for y. You can take a partial with respect to s, or a partial with respect to t. And the same thing for z. You can take a partial with respect to s, or you can take a partial with respect to t. Okay, so there's a lot more paths or branches that we can travel along in this diagram, so you can imagine that our formulas for the chain rule are going to look different than what we have used so far. And this is why I recommend that you draw this tree, because it will help you modify the chain rule formula for the specific problem you are working on. And in this case, there will be two chain rule formulas, because we will have to find a partial derivative of w with respect to s and with respect to t. And even if the problem didn't tell us this, if it just said use the chain rule to find the derivative or derivatives, you would know that you have to find two in this case, or two partial derivatives specifically, because there are two independent variables in the expressions for the intermediate variables. Okay, so always pay attention to the number of independent variables. That's very important when you're using the chain rule. But now let's set up the formulas, starting with the partial derivative of w with respect to s. What would that be equal to? Well, what we want to do is trace along the paths that lead us from w to s throughout the tree. So one of those paths would be this path right here that takes us from w to x to s. So we'll take a partial of w with respect to x, and then take a partial of x with respect to s. And that is a partial, not a regular derivative, because we have a choice here. We could go to s or t from x. There's not just one derivative that we could take, there are two different ones that we could take, so they are partial derivatives. All right, so we have the partial of w with respect to x multiplied by the partial of x with respect to s. And then we will add that to the next path that would take us to another s within the tree. And so another one would be this path here from w to y, and then from y to s. So we would take a partial of w with respect to y, and then multiply that by a partial derivative of y with respect to s. So you'll have a partial of y with respect to s. And then we still need to add another term, because there's another path that will take us from w to another s, and that would be this path right here, from w to z, and then from z to s. So we would have a partial of w with respect to z multiplied by a partial of z with respect to s. So we'll have a partial of w with respect to z multiplied by a partial of z with respect to s. Okay, so that's one of our formulas That's for a partial derivative of w with respect to s, but now let's write out the formula for the partial of w with respect to t. It's going to look very similar, except instead of having these partials with respect to s, they will be partials with respect to t. Okay, so the partial derivative of w with respect to t will be equal to a partial derivative of w with respect to x, and then a partial of x with respect to t. Right now we want to travel along the paths that will take us to the different t's within the tree. So we go from w to x, and then from x to t. So we get a partial of w with respect to x again, multiplied by a partial of x with respect to t, and then we will add that to the next term that we'll get from the next path that takes us from w to t. So that would be this path where we go from w to y and then from y to t. So we'll take a partial of w with respect to y and then take a partial of y with respect to t. So we have a partial of w with respect to y multiplied by a partial of y with respect to t. And then finally, we have one more term because there is one more path from w that takes us to a t, and that would be this path right here from w to z and then from z to t. And so that would be a partial of w with respect to z and a partial of z with respect to t. So we have a partial of w with respect to z multiplied by a partial of z with respect to t. All right, and so there are the two formulas for the chain rule that will allow us to find the partial of w with respect to s and the partial of w with respect to t. All right, so let's work on them here. Let's do one at a time, starting with the partial of w with respect to s. So to begin that, we have to take a partial of w with respect to x. So looking at w here, we will treat y and z as constants. So y squared and z squared are constant terms whose derivatives are 0, but then the derivative of x squared is 2x. So we have 2x multiplied by the partial derivative of x with respect to s. So looking at x here, s is part of the sine function, so we want to take the derivative of that and leave this t alone. That's just a constant with respect to s, so it's just the coefficient of the sine function. And the derivative of sine is cosine, so we get t times cosine s. All right, then we'll add that to the partial of w with respect to y. So looking at w, x squared and z squared, we would treat as constants. Their derivatives are 0, and the derivative of y squared is 2y. So we have 2y times the partial derivative of y with respect to s. So looking at y here, s is inside the cosine function, so take the derivative of cosine and leave this t alone. The derivative of cosine is negative sine, so we have negative t times sine of s. All right, and then that will be added to the partial derivative of w with respect to z. So just take the derivative of this z squared. Both y squared and x squared would be constants whose derivatives are 0, and the derivative of z squared is 2z. So we have 2z multiplied by the partial derivative of z with respect to s. So looking at z here, s is to the first power, so its derivative would be its coefficient, or the constant multiplied by it, which would just be t squared in this case, so we're multiplying by t squared. All right, and so we'll simplify that then. Let's just move right on to the partial of w with respect to t, and then we'll come back and simplify both of these partial derivatives. So for the partial of w with respect to t, we start with the same partial derivative of w with respect to x, which is 2x. We already found that earlier, so we can just reuse our work. We have 2x, and that will be multiplied by the partial derivative of x with respect to t, which we have not done yet, right? Last time we did the partial with respect to s, now we have a partial with respect to t. So looking at x here, t is to the first power, so its derivative would be its coefficient, or the constant multiplied by it, which would be sine s in this case, because we're treating s as a constant when differentiating with respect to t. So we multiply by sine s, and then we'll add that to the partial derivative of w with respect to y, which we already found earlier. It's 2y, so let's reuse that work. We have 2y multiplied by the partial derivative of y with respect to t. So looking at y here, once again we have t to the first power, so its derivative would be its coefficient, or the number multiplied by it, which in this case is cosine s. That would be a constant with respect to t, because we'd be treating s as a constant. So we have cosine s, and then we will add that to the partial derivative of w with respect to z, which we already found. It's 2z, so we have 2z multiplied by the partial derivative of z with respect to t. And so looking at z here, s is a constant, so leave it alone. and then t squared, you can find the derivative of that using the power rule for derivatives. So multiply that 2 down, subtract 1 from the exponent, and you get a derivative of 2s times t to the first power. Okay, so now we have our two partial derivatives of w with respect to s and t. Now we just want to simplify them, and so let's work on that here. Starting with the partial of w with respect to s, we will get 2xt times cosine of s minus 2yt times sine of s plus 2zt squared. All right, now you could leave your answer here, that would be fine, but if we were to get this entirely in terms of t, there are some nice simplifications that we can make. These are not incredibly difficult expressions to work with for x, y, and z, especially considering where they are within this expression. And so let's plug them in. X is t times sine s, so I'm going to put that in right here for this x, and we will have that this is equal to 2 times t sine s times t times cosine s. But now we have a t here and a t here. Multiply those together, and you get t squared. So I'm just going to rewrite this here. We'll have 2 times t squared times sine of s times cosine of s. And then we have minus 2 times y, which is t cosine s. That t will be multiplied by this t. So you'll have another t squared multiplied by sine s cosine s, right? We still have this sine s here, and then part of this y is that cosine s. So I just put it over here. And then we have plus 2 times z, which is st squared multiplied by t squared. So what we get there is st to the power of 4. And notice what happens here. These two terms are exact opposites of each other. We have positive 2t squared times sine s cosine s and negative 2t squared times sine s cosine s. So those two terms cancel out, just giving you that the partial derivative of w with respect to s is equal to 2st to the power of 4. That is one of our partial derivatives here. It simplifies very nicely. But now what about our other partial derivative, the partial of w with respect to t? Let's simplify this next. This will be equal to 2x times sine s plus 2y cosine s plus 4zst. All right, and so once again, let's plug in what x, y, and z are equal to from these equations. Starting with this term here, we have an x, which would be replaced with t times sine s. So this is equal to 2 times t sine s times sine s. So there's two sine s's now. We can multiply those together and get sine squared s. So I'm just going to rewrite that right away. What we have here is 2t times sine squared s, and then we have plus 2 times y, where y is t cosine s. So we have t cosine s times cosine s. But once again, we have a cosine s and a cosine s, just like we had two sine s's. And so you can multiply those together and get cosine squared s. All right, so I'll do that right here, cosine squared s. And then we have plus 4 times z, which is st squared. So we have st squared times st, and we'll simplify that then. But over here, something that's really cool that maybe you noticed, maybe not, but if you didn't, you're going to see it now. If you pull out a common factor of 2t from these two terms, look what you're left with. 2t times sine squared s plus cosine squared s. That right there, we know is equal to 1 from the Pythagorean identity for sine and cosine. So that whole thing is just 1 times 2t, which is 2t, which is a very nice simplified term that is then added to this term, where we have s times s, which is s squared, and then t squared times t, which is t cubed. So we have 4s squared t cubed, which means that our final answer here is that the partial of w with respect to t is equal to 2t plus 4s squared times t cubed. All right, that is the other partial derivative for this example. And so with that, we're done. We have now found both of the partials of w with respect to s and t. Next up, we want to find the partial of w with respect to s and the partial of w with respect to t using the chain rule. And we are given that w is equal to x times arctangent of yz, where x is equal to the square root of s, y is equal to e to the power of 2t, and z is equal to t times cosine s. Okay, so this is very similar to our previous example. We just have different expressions for w, x, y, and z, but I do think it's still important that we set up the derivative tree to help us form our chain rule formulas. And so let's do that here. We still have one dependent variable of w, and then w is in terms of three intermediate variables of x, y, and z. So I'll write those down. We have x, y, and z. And so you can take a partial derivative of w with respect to x, y, and z. But then let's take a look at each of these intermediate variables and what they are equal to. X is just defined in terms of s, right? We have the square root of s, and that's it. There's no t's there. So in the tree, just draw a branch out for s. There's no reason to draw one out for t in this case because there are no t's in that expression for x. And then if you look at y is just in terms of t, right? We have e to the power of 2t. There are no s's, so for y, we'll just have a branch for t. And then finally for z, z is defined in terms of both s and t, so there will be two branches for z. Z is connected to both of the independent variables of s and t. All right, so our tree looks a little bit different here. So our formulas might look a little bit different as well. And so let's set them up. Let's start with the formula for the partial of w with respect to s. So what will that be equal to? Well, we want to travel along all the paths that lead us from w to s. So we have one right here where we go from w to x to s. And so we'll take a partial of w with respect to x and then a partial of x with respect to s. Now, you might be tempted to say, well, we're taking a regular derivative of x with respect to s because there are no options here. But since there are other independent variables present in the other intermediate variables, technically we still want to take a partial derivative with respect to that independent variable for x. Okay, because technically you could draw a branch to t for x, but when you take the partial derivative of x with respect to t, you're just going to get 0. Because there's no t's here, the square root of s is just a constant, so its derivative is 0. So that partial derivative really doesn't even exist. That's why I didn't write it there. It makes our tree a little bit simpler to look at. And that partial derivative being 0 will come into play later, and so stay tuned for that. But let's just write out the first term for this partial derivative using this path. We're taking a partial of w with respect to x, and then multiplying it by a partial of x with respect to s. And then let's add that to the next term, which you would think would be based on y, but as you can see here, y does not have a path to s, because y is just in terms of t. All right, so what's going on here is that just like x technically has a path to t, y would also technically have a path to s. You could take a partial of y with respect to s, but since y doesn't have any s's, this whole thing is a constant and its derivative is 0. Okay, so you could take a partial of w with respect to y, but then you would be multiplying it by a partial of y with respect to s, which doesn't exist. It's 0. So that whole middle term would just be 0. All right, there's no need to take a partial of w with respect to y and then multiply it by the partial of y with respect to s because the whole thing is just 0. Okay, but then we still need to account for the third term, which we would get by traveling along the path from w to z to s. All right, so that would be this path right here. So we'll take a partial derivative of w with respect to z, and then multiply that by the partial derivative of z with respect to s. All right, so that will be our partial derivative of w with respect to s. But then what about our partial derivative of w with respect to t? What will that be equal to? Well, the first term you would expect to be based on x, and you could certainly try that. You could take a partial derivative of w with respect to x, but then the partial derivative of x with respect to t, as I've talked about earlier, would be 0. So that first term is completely unnecessary. It would just be 0. X is entirely defined in terms of s, so the partial derivative of that with respect to t would be 0. And so multiplying that by the partial derivative of w with respect to x just results in a 0 for that term. Okay, so let's just move on to the second term here, which would be based on y, and we can take a path from w to t in this case. We'll take a partial of w with respect to y, and then a partial of y with respect to t. So that will look like this. We'll have a partial of w with respect to y times a partial of y with respect to t. And then finally, for the last term, we can take the path from w to z to t. That would be this path right here. And so we'll take a partial of w with respect to z, and then a partial of z with respect to t, giving us this term, the partial derivative of w with respect to z, multiplied by the partial derivative of z with respect to t. Okay, and so now we have our formulas for both of our partial derivatives. Now let's work on finding them. It's going to be a little bit easier than it was in the previous example because we have one less term to worry about in each case because some of those partial derivatives would be zero. All right, and so let's start with the partial derivative of w with respect to s, which means we first have to find the partial of w with respect to x. And so looking at w here, x is the coefficient of arctangent of yz, which with respect to x would just be a constant. So that would actually be the derivative of x to the first power. We will get arctangent of yz multiplied by the partial of x with respect to s. So looking at x here, it is entirely in terms of s. So that will be a simple enough derivative to take. Remember that the square root of s is the same as s to the 1/2 power. So the derivative of that using the power rule for derivatives is 1/2 times s to the negative 1/2 power. And then we'll add that to the partial derivative of w with respect to z. And so this is going to be a little bit more complicated because now z is inside the arctangent function for w here. So we will have to take the derivative of the arctangent function. And so remember from Calc 1, if you take the derivative of arctangent of u, that is equal to 1 divided by 1 plus u squared times u prime. Right? It's 1 divided by 1 plus that inside function squared times the derivative of that inside function. So if we do that here, we still have that x being multiplied by that derivative. So keep the x in the numerator, and then you'll have that divided by 1 plus the inside function, y times z squared times the derivative of yz, that inside function. And with respect to z, the derivative of yz would be y. Because z is to the first power, its derivative is its coefficient. So you would be multiplying by y, but I'm just going to put that y in the numerator here. So we will have x times y divided by 1 plus yz squared. Okay, and then we want to multiply that by the partial derivative of z with respect to s. And so looking at z here, s is inside the cosine function, so you want to take the derivative of cosine and leave this t alone. So we will multiply by negative t times sine s, because the derivative of cosine is negative sine. Okay, so that's our partial of w with respect to s, at least without simplifying anything. We'll do that in just a little bit. But first, let's work on the partial of w with respect to t, starting with the partial derivative of w with respect to y. And so looking at w again, y is inside the arctangent function, so we still have that constant of x divided by 1 plus the inside function squared, so yz squared, multiplied by the derivative of the inside function, which now with respect to y would be z, because the derivative of y to the first power is its coefficient, or the number multiplied by it, which would be z. So in the numerator, instead of just x, we will have x times z. All right, and then that will be multiplied by the partial derivative of y with respect to t, and y is equal to e to the power of 2t, and so the derivative of that exponential function would be itself, but then multiplied by the derivative of the exponent, and the derivative of 2t is 2. So we get 2e to the power of 2t plus the partial derivative of w with respect to z, which we've already done before. So let's just rewrite that. We have xy divided by 1 plus yz squared. We don't need to do that again. We already did it before. But then we do want to multiply it by the partial of z with respect to t. So looking at z here, we have t times cosine of s. The derivative of t to the first power is just its coefficient, or the constant being multiplied by it, which in this case would be cosine of s, because s would be a constant with respect to t. So we're multiplying by cosine s. That would be the partial derivative of z with respect to t. All right, and so now we have both the initial calculations for these two partial derivatives. Now let's simplify them. Starting with the partial of w with respect to s, this s to the negative 1/2 power could be moved to the denominator of this term, and then you can change it to be the square root of s. So this would be equal to arctangent of yz divided by 2 times the square root of s plus, or really it would be minus, if you multiply this into the numerator, that negative will come out front. So let's erase that and write minus x times y times t times sine s divided by 1 plus y squared z squared. Right, you can square both y and z inside that quantity, and this is what you would get. And that's it. I'm going to leave it in this form. There is no need to get this in terms of t. That would be very complicated when you consider what x, y, and z are equal to in terms of the independent variables. Replacing x, y, and z in this expression with those expressions would get very complicated very quickly, so don't worry about that here. This would be the partial derivative of w with respect to s. Just remember that x, y, and z are all equal to these expressions here. All right, and then for the partial of w with respect to t, if we simplify, this will be equal to 2x times z times e to the power of 2t divided by 1 plus y squared z squared plus x times y cosine of s divided by 1 plus y squared z squared. But notice that these two terms do have a common denominator, which is pretty nice, so we can combine the numerators, and that would be our final answer. So I'm just going to do that like this. I'm going to erase that denominator, put a plus sign between those two terms, and then divide them by that denominator of 1 plus y squared z squared. That would be the partial derivative of w with respect to t. Okay, once again, I'm not going to get this entirely in terms of the independent variables because that would be way too complicated given how many x's, y's, and z's are in this expression and the actual expressions that they are equal to in terms of those independent variables. Okay, so this answer is fine. We have now found both of the partial derivatives of w with respect to the independent variables s and t. Let's take a look at one more example for this video. All right, so for our last example, we want to find the partial derivative of w with respect to t using the chain rule. And we are given w is equal to x squared times y plus y squared times z, where x is equal to rst squared, y is equal to rs cubed t, and z is equal to r squared s t cubed. Okay, so in this problem, we only want to find one partial derivative of w, specifically with respect to t, which if you noticed is just one of three independent variables, right? W itself is defined in terms of three intermediate variables. We have x, y, and z, but then each of those intermediate variables, x, y, and z, are all defined in terms of three independent variables, r, s, and t, which is pretty wild. And thankfully, we don't have to find all the partial derivatives of w, although we could, because there would be three of them, one for each of those independent variables. We would have a partial of w with respect to r, s, and t, but in this case, we just want to find the partial with respect to t. Okay, and so to help us find that, I think it would be very helpful for us to draw one more derivative tree. We still have the same dependent variable of w, and then three intermediate variables of x, y, and z. So write in x, y, and z, and then I will connect all three of those. You can take a partial of w with respect to each of those intermediate variables, but then for each of the intermediate variables, there are three independent variables. So from x, we can draw three branches, from y, we can draw three branches, and from z, we can draw three branches. All right, one of those independent variables is r, another one is s, and the final one is t. Okay, so if we want to find the partial derivative of w with respect to t, really all we're focused on here are any paths that lead us from w to t. Okay, we don't care about r or s in any of these branches. We're just worried about what's going to get us from w to t. Okay, so let's set up that formula. We'll have the partial of w with respect to t is equal to the first term, which will be based on x. All right, we're going to take the path from w to x to start. So that will be this path right here. And then we'll go from x to t. So we'll take a partial of w with respect to x, and then a partial of x with respect to t. So we have a partial of w with respect to x times a partial of x with respect to t. Then we will add that to the next term, which will be based on y. Let's take this path next, because we can go from w to y, and then from y to t. So we'll take a partial of w with respect to y, and then take a partial of y with respect to t. So we have a partial of w with respect to y multiplied by a partial of y with respect to t. And then finally, we have one more term based on z, because now we will take this path, we'll go from w to z, and then from z to t. So we'll take a partial of w with respect to z, and then a partial of z with respect to t. So we have a partial of w with respect to z multiplied by a partial of z with respect to t. Okay, and so now we're good. That is the formula for the partial of w with respect to t. Now we can work on finding it. Again, there would be two other partial derivatives of w that we could find, but for this example, we just want to find one of them. And so let's work on it here. Let's start by finding the partial of w with respect to x. So looking at w here, y would be a constant, so ignore that y, and take the derivative of x squared, which would be 2x. So we get 2x times y, and then for the second term, there are no x's there, so that's a constant. Its derivative is 0. So that's the partial of w with respect to x, but that will be multiplied by the partial of x with respect to t. So looking at x here, r and s we would treat as constants, but take the derivative of t squared by multiplying that exponent down and subtracting 1 from the exponent. So we get 2 rst to the first power. Then we'll add that to the partial derivative of w with respect to y, and so y is in both of these terms, so you do want to take that into account. For the first term, y is to the first power, so its derivative would be its coefficient, which would be the constant of x squared. Since we're differentiating with respect to y, x is a constant, so we have x squared, and then for the second term, y is to the power of 2, so use the power rule there and ignore that z, just keep it with the term. You'll have plus 2y times z, that is the partial of w with respect to y, and then you want to multiply that by the partial of y with respect to t. And so looking at y, t is to the first power, so its derivative would be its coefficient, which would be r², because those would be constants with respect to t. So we get r times s². And then finally, we will add that to the partial derivative of w with respect to z. And so looking at w, the first term would be 0, because x squared times y would be a constant with respect to z. Its derivative is 0. And then for y squared z, z is to the first power, so its derivative would be its coefficient of y squared. So we have y squared multiplied by the partial derivative of z with respect to t. And so looking at z here, r squared and s would be constants, so leave those alone, and take the derivative of t cubed. Multiply that 3 down, and subtract 1 from the exponent. If you do that, you'll get 3r² times st squared. All right, and then finally, let's just simplify a little bit. 2 times 2 is 4, and so we get 4xy rst plus this term, but bring that rs³ out to the front. Or I suppose you could distribute it through this quantity. I guess I'll do that here. We'll multiply rs³ by both of these two terms. That will give us x² times rs³ plus 2yz rs³. And then we have plus y² times this expression, which will simplify to be 3y² r² st². All right, and that's it. I'm going to leave it there. That is the partial derivative of w with respect to t. As you can see, there's a lot of x, y's, and z's in this expression, and so I'm not going to bother with substituting what they are equal to in terms of the independent variables. You could do that here. It wouldn't be too difficult because these are fairly simple expressions for x, y, and z. But there's no need to do that here, since we just wanted to find the partial of w with respect to t, and we weren't told explicitly to get it entirely in terms of the independent variables. So I'm just going to leave it like this, but if you want to, you could replace x, y, and z with these expressions. Okay, but with that, that is it for this example, and this was the last example for this video. But if you want to get some more practice using the chain rule for multivariable functions, I do have more available on my membership site. So if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.